Next, we're going to talk about some very basic time series models. Essentially, these models will form, let's say, the building blocks of more complicated models that we will examine during this course. So to begin, though, we need to talk about some basic definitions as well. So first of all, a stochastic process is just simply a collection of random variables, let's call them x of t, indexed by t. This t does not have to correspond to time, but it will for at least how we're using a stochastic process. So a special case of a stochastic process is called a time series for us, and it's a collection of random variables that are indexed by time. So for example, we could let x of t, where x is a capital letter to denote that it is a random variable. This is using the same kind of notation that you would see in a mathematical statistics course. So let capital X sub t be a random variable at time t. So capital X1 is a random variable at time 1, capital X2 is a random variable at time 2, and so on. Then we can have a realization of these random variables. In other words, we can go out and take a sample and we can obtain the observed values of these random variables. This is called a realization. These observed values, again using the notation that you would typically see in a mathematical statistics course, are denoted by lowercase letters. So lowercase x1 is the realization at time 1 for variable x. Or lowercase x sub 2 is the realization of the random variable at time 2, and so on. Now, even though I went through the process of talking about capital X's and lowercase x's here, we will actually not use that formal notation that you would see in a mathematical statistics course. Rather, once you get beyond intro mathematical statistics courses, and especially what you would see in a time series analysis textbook, some of the formality is, let's say, thrown away, and we're just simply going to, in our class, use simply lowercase x's. And the reason being is because now that you've progressed beyond a intro course, it should be clear to the student, the viewer of this video, in the context of the problem, if we're dealing with a random variable or an observed value. So for example, if one said expected value of, and a little x1 there, or lowercase x sub 1, if I'm taking an expectation, it should be clear that I'm dealing with a random variable, even though I have a lowercase letter there. So again, most time series analysis textbooks typically just simply use lower cases all the time, and I'm going to just adopt the same convention here. Okay, so the first model for time series data that we can look at is referred to as a white noise model. My corresponding stuff that I'm going to do in R is in the file or the program white_noise.r. This name white noise comes from actually engineering, and in particular dealing with acoustics. You know, often you will hear, let's say maybe on the radio or maybe some other kind of audio situation, maybe a bunch of static. That's often referred to as white noise. Engineers refer this to mean that there is actually no pattern at all amongst how that noise comes about. And essentially, that's what this is going to mean to us. That it's a special kind of time series that's a collection of independently and identically distributed random variables. We're going to assume that we have a constant mean of 0, and also a constant variance where we don't have to necessarily state what the variance is, just that we have a constant variance. We could write this in terms of typical statistical notation as, let's say, our random variable for our white noise process is W, indexed at time t. The tilde there means distributed as, so WT is distributed as independent random variables. And then in parentheses, we put what the mean is, and also we put what the variance is. So the mean is 0, and the variance is some number. We don't know what it is. We're just going to call it sigma squared sub W. And every WT in our white noise model here has the same variance for t equal 1 to n. Now, very often we will associate a particular probability distribution with this as well. And so, for example, if we said a normal distribution, then we would use the common notation where we put an n in front of those parentheses there. So what does this all mean? It just basically means we have a collection of random variables, a time series, W1 through Wn. Each of them have the same distribution, and each of them are independent of one another. So then, given the setup corresponding to what we've seen previously, what we might be interested in asking, well, what patterns would you expect over time here? How can the dependence among observations be used to help model the corresponding data that we get? And in the end, actually, the patterns are, well, there is no pattern. Everything's completely at random here. There is actually no dependence because everything is independent and identically distributed, or IID. You might have heard that expression before. And so you might be thinking, well, why are we looking at this? We can't use, let's say, W1 to help predict W2. But what I said a few minutes ago is that we're actually kind of putting together the building blocks of these models. And so having a white noise part of a model is very common in time series analysis. So how can we actually simulate a white noise model, or you could say a white noise process, because it's a stochastic process, just the common terminology that people use here? Well, we can use the same techniques that you should have learned in another class about how to simulate data from a normal distribution. So let's say that we have n as equal to 100. So we're going to have 100 observations from this white noise process, this white noise model. And because I need to specify a particular variance, suppose sigma squared W is equal to 1. So let me jump on over here to 10 to do this. Then, so to simulate data, or to simulate the data, I'm going to use the R norm function. R stands for random, norm for normal. And I'm going to simulate a sample of size 100. So my n argument is 100. Mean equals 0. And our norm doesn't accept a variance argument. Instead, it accepts a standard deviation argument. So if the variance is 1, standard deviation is 1. So SD is equal to 1. And I'm going to put the results into W. And if I look at the first 6 observations in W, this is what we get. Now, if I were to run this exact same code again, notice, since I'm simulating the data in a random manner, I don't get exactly the same thing. But at least for instructive purposes, it's nice at times to be able to get the same set of observations. So what I'm going to do right before I run the rnorm function, I'm going to set a seed. What this tells R is that whenever I simulate the data from the normal distribution, and R's internal algorithm to do this, I'm basically always going to start at the same spot. So I just simply chose a number off my head, 8128, as my seed number, so that every time that I actually run this segment of code here, I'm always going to get exactly the same thing, and it allows us to be able to reproduce the results. Okay, so now let's, so here's actually the whole W here. So you can see that W1 is negative 0.1, W2 is 0.2554, W3 is 0.82065, and so on. Let's plot this now as a time series using methods that we've seen before. So I'm going to open up a new graphics window. to do the plot. Again, I don't have to do this. I can use just the same graphics window, maybe perhaps I've been using previously in my session. I'm going to open up a new one here. The way that I can open it up is to use the dev.new function for device new. And here we go. And always, for some reason, R opens it up in a different monitor that I'm using at my desk. So here's the actual graphics window. And then I'm going to plot then the corresponding data using methods that we've done before with the plot function. And let's actually take a look at that graph. And here we go. So some comments about this plot. First of all, notice for my y-axis here, I've labeled it as WT because we're observing this information from this white noise model here, or white noise process. But notice how I got a subscript there for W. Well, to do that, I can use in R the expression function as part of my ylab argument, ylab standing for y label, y-axis label. And what this expression function allows me to do is put mathematical expressions on a plot like this. And so within expression, I have W, and then to do a subscript, simply I use the square brackets and I put T inside it. So that's how I got the W sub T. Now also on this plot, you'll notice that I have a title here, white noise, where WT is distributed as independent, normal 0, 1. How did I get that on my plot? Well, I used the main argument for the plot title. Once again, I use the expression as well. But now, since I have a mixture of some mathematical expressions like W sub T and some regular text, what I'm going to do is paste together my regular text with the WT and the independent normal 0, 1. So I use the paste function to do that. Okay. So here's my corresponding plot. If you notice in my code, I use type equal O. That again provides now both the lines and the points on the plot simultaneously. I could also plot the points separately, plot the line first and then plot the points separately, again using methods that we've seen before. And here is my corresponding plot as well. Okay, so let me come back over here to Word. So what patterns do we see over time? Well, this is a white noise process. Everything comes about through independence, through this normal distribution with mean 0 and a variance of 1. So notice what we see here is that most of the observations are between -2 and 2, which you would expect from a normal distribution. But because of that independence there, we can see this a lot of oscillation, you could say, between the points. We don't necessarily see any kind of constant pattern that's happening throughout this plot here. And so in the end, again, we don't have dependence amongst our observations. We'll look at how we can actually numerically measure that dependence later. But we don't have any dependence amongst our observations. So in the end, we're not going to be able to really model this data very well, other than knowing, the observations tend to fall between -2 and 2, and they seem to be centered at 0. Well, what if I were to actually, let's say, simulate another white noise process and compare it to the one that we just looked at? So I could do that. I'm going to set a new seed number, and then I'm going to put the results into a new object called w.new. And then from that, let me actually do this in R here. And then from that, then, what I'm going to do is plot my original data with the points on it, and then plot my new data that I just got from w.new using the lines function and also the points function again. And I'm going to put a nice little legend on top of my plot as well. And here's what I get. And what we can see here is that both time series, observed values of our time series, aren't following any particular constant pattern between the two, other than the values are between -2 and 2 and centered at 0. So this again, helps us see that, these observations are essentially independent of one another. Okay, so on your own, you can take a look at how we can actually plot the two time series separately. I do that here. The way that I get the two separate plots within one graphics window is I use the function par, which stands for graphics parameters, and I say make frame by row. I want 2 rows and 1 column of plots. Okay, so again, this white noise process, this white noise model, is going to provide a building block for us when we construct more sophisticated models that are actually useful. So let's take a look at another example. This example deals with what's called a moving average. The corresponding stuff that I do here is in my movingaverage.r program. So the purpose here is now to show you how we could have some, let's say, dependence from one observation to the next. And we're going to do this through this thing called a moving average. You'll see why it's called a moving average shortly. And what you're also going to see on the corresponding plot is that when we graph this moving average result, we have some, let's say, smoothing done to our line that we're seeing on our plot, meaning it's not going to oscillate up and down as much. It's going to, you're going to start seeing some patterns that occur in the plot. So our moving average, we're going to define it mathematically as m sub t, so the moving average at time t. And simply what it is an average of 3 of our w's, where we start at wt, we go to wt minus 1, so 1 time period in the past, and also wt minus 2, in other words, 2 time periods in the past. So what that means then for us is that, let's say m sub 3 is equal to w3 plus w2 plus w1 divided by 3. Similarly, real fast, m sub 4 is now w4 plus w3 plus w2 divided by 3. And so we would expect then m3 and m4 to have some kind of dependency. We would expect them to be correlated to one another, because notice that they share some parts in terms of how the actual m value comes about. And so if they share those parts, we see some dependence, we see some correlation. So you might think, okay, well, whatever I get for m3 might help me understand what m4 should be. Okay, so let me come over here to 10. So to simulate then this corresponding moving average, I'm going to again get my white noise that we had previously. And then to actually get the m, there's a number of different ways to do that. I'm going to actually use a function called filter. And basically what this is more formally called a linear filter, which allows me to simply take a linear combination of items in my W that I have there in the format that I want to for a moving average. So if I say filter, what do I want to filter? I want to filter W. I want to put it through this, basically this set of linear combinations of these W's. And then oddly, for this function itself, there's an argument called filter. And what I want to do for this filter argument, I want to put, basically, I want to create 3 values that are each equal to 1/3. And the reason being is because, if I come back over here, of course, we could rewrite this m sub t as 1/3 times wt plus 1/3 times wt minus 1 plus 1/3 times wt, I'm running out of room, wt minus 2. So in other words, the filter argument says, okay, what are the coefficients on our w's here? And if I come back here, So yeah, so the REP function, if you haven't seen that before, stands for repeat, and I want to repeat 1/3 3 times. Sorry, I should have said that at the very beginning. Excuse me. Now, how do I want to do this filter? Well, the argument value that I'm going to use is convolution. And in R's terminology for the filter, that means basically what I want to do is I want to, basically apply this to my W's, this particular filter, in the form of a moving average. And then sides equal 1 says, okay, I want to start, let me come back here. I want this index here, m sub t, to match up with the very first element that I have in my moving average. You know, there are other moving averages that one could define, although this wouldn't be useful for us. You could define a moving average like this, where you take one time period into the future, wt plus 1, and then you have wt and wt minus 1. You could do a filter like that as well. That won't be useful to us. Instead, we're going to use the filter as shown, or use the moving average as shown there. Okay, so let me go ahead and apply that. And so what we have here returned, here are the first 6 values in our moving average. And so m sub 3 correspond to what I had written before, W1 plus W2 plus W3 divided by 3, 0.32365, or 0.3236. Notice I cannot have a M1 and I cannot have an M2, because then that would rely on like a W0, a W negative 1, which we do not have. And so let me just come over here in Word to do this. So I go ahead and plot, excuse me, I go ahead and plot the moving average on top of the white noise observations that we saw previously. And this is what I get. So the moving average is in the darker red, or I think it's actually a brown. And so this first point here in the moving average is an average of these 3 blue points that we see on the screen, or highlighted. And so earlier I said that this moving average has you could say a smoothing effect, and you can see that to some respect on this plot, because this dark brown line, or this thick brown line, is not oscillating as much as what we had seen previously with the white noise. You know, we start seeing some patterns. You know, we see some consistent things happening here in this plot over time. And that's because since we're combining multiple observations together, and each of these moving average values contains some of the same observations. Also, something that you will see in this plot is that notice that the highest points on the brown line don't necessarily go up as high. The lowest points don't go as low as much as what we saw with that white noise process as well. And that's again comes about because we're taking averages of multiple points over time. So what patterns are there over time? Well, again, you know, now that we are combining multiple observations together, you know, if I were to look at, let's say, M4, I have a general idea where M4 would be based upon what M3 is. Similarly, I have a general idea where M5 should be based upon where M sub 4 would be, where M sub 3 would be as well. So now this dependence here potentially could help us construct a nice a nice model to help predict what current values are and what future values are as well. So, you know, I guess foreshadowing some stuff that we will do in the future when we do actual forecasting. You know, so here's M sub 100. You know, based upon what we see in this plot, you know, we would probably, excuse me, we would probably expect m sub 101 to be somewhere right around here. We would not expect it to be up there. We would not expect it to be down there. So what we just saw was what's often referred to as a 3-point moving average, because we used the 3 of the W's together to form that average. You could use more or you could use less points. So a 7-point moving average is what's shown in this plot here. You can see the corresponding code in my program. The 7-point moving average is the green lines there. And again, we start seeing even more smoothing compared to what we saw with the brown before. Also, we know that we can see it, the range of the possible values here for the green is less than what we saw with the brown, and it's even further less compared to what we had for the white noise as well. And so as more and more points get added to the moving average, we're going to see a smoother and smoother effect until eventually, let's say if you have a 100-point moving average, well, that wouldn't be very fun, but you could have a 100-point moving average, and you would expect that value to be approximately 0. So the last example that we're going to look at for these basic models that we will see in this course is what's called an autoregression model. And so, the name regression, all of you should be familiar with it. Here's a regression model that you would see in a regression course. Y sub I is equal to beta 0 plus beta 1 times x sub I plus epsilon sub I. This epsilon sub I is distributed independent, normal 0 sigma squared. Also, we could have, let's say, I equal 1 to n. This x of I is our explanatory variable or independent variable. The beta 1 is our parameter, is a parameter that we would want to estimate. It's the slope coefficient on x. Beta 0 is also a parameter that we would want to estimate. It is the y-intercept term. And y sub I is our response variable or dependent variable. So that's a regular old regression model. Now, what we're going to look at is an autoregression model. The name auto, I don't mean that in terms of like a car. Rather, what I mean that is like it's the dependent variable is self-dependent on previous observations for that same variable. That's where the auto comes in. And so this is what one potential autoregression model looks like. X of t plays the role of y. X of t minus 1, meaning one time period in the past, that's going to be used as like an explanatory variable or independent variable to help you get what x of t actually is. So for example, let's say maybe that x represents a child's height. And maybe t is measured at, let's say, years. So the child's height at year 3 is going to be dependent upon what the child's height was at year 2, and so on. That might be not necessarily be the best example. Let's actually look at a different one real fast. So for example, maybe at Starbucks, we are interested in the number of customers that a particular location has, and maybe it could be modeled using an autoregression model, where let's say t is a particular day, so t equal 1 corresponds to day 1, t equal 2 corresponds to t2, and so on, so that x of 2 at day number 2 is going to be equal to 0.7 times what occurred for the number of customers at day number 1. That's how we say that x of 2, the number of customers at day 2, comes about. But we also know that it's not going to be a perfect predictor, so we put a corresponding error term with it, which in our terminology is our white noise process. So the WT again is distributed independent, normal 0. In this particular case, I chose a variance of 1. So the WT now corresponds to epsilon there. Okay, so that's an autoregression model. It can be very useful in many situations because, again, what happens in the past you would think might be helpful for the future. So I talked about the example with Starbucks, but you could also think of maybe X of t as stock price as well. What the stock price is today is dependent upon what the stock price was previously, plus some random noise. Okay, so I've already basically written this concept out, that x2 is dependent upon x1, x3 is dependent upon x2, but also because x2 comes from x1, it's also dependent upon x1, and so on. Obviously, we will have correlation between these random variables. So next, let's talk about one way to actually simulate observations from an autoregressive model like this. So let me come over here to this particular program. It's called AR1.R. And again, I'm going to come up with some of my white noise. This is a different white noise set of observations than what we had before because I use a different seed number. And what I would like to do is simulate, first of all, 200 observations from this model. And the way that I'm going to do that is to use a for loop. If you're not familiar with for loops, I'll talk about that more in about a minute. But since I want to simulate 200 values, I need a place to store these 200 values. And so what I'm going to do in terms of R's terminology, I'm going to create a vector that's essentially empty. The way that this can be done is use the numeric function, and I want to have a length of 200. I want a vector of length 200. And R initializes these values with simply zeros. So that's where I'm going to put everything. Let me come back over here. Okay. Excuse me. Now, what is x1? x1 is equal to 0.7 times x0 plus w1. Now the problem is I don't know what that x0 is to start this simulation process. x2 is going to be equal to 0.7 times x1 plus w2. So whatever I get for x1 is going to go in there. x3, 0.7 times x1 plus w3. But again, I need a place to start. So what I'm going to do is I'm going to initialize an object. I'm going to call x dot 1, which is going to have a value initially of 0. I could have chose a different value if I wanted to. I decided to make it 0 because in the end, as you'll see from some other stuff that we'll do this semester, I want these x's to have a mean of about 0. So I'm going to start with putting 0 in there. Once I have that, then I can basically follow the same process of simulating or come up with these observations. And the way that I do that is through what's called a for loop. For loops or do loops, or there's a lot of other looping structures that exist in programming languages. We typically work with just a for loop. A for loop allows you to basically do this process. So find x1 for, let's say, iteration 1, then go to x2, find x2 for iteration 2, and keep on doing this all the way down to x200, which will be this. Okay, so in R's syntax, a for loop is done with a for function. Inside this function call, inside the parentheses, I'm going to create an index called I. And I want I to range from 1 to the length of x, which happens to be 200. And then do the following that you see inside these curly brackets. So the first time through this loop, when I is equal to 1, what's going to happen is that 0.7 times x dot 1, which I set to be 0, plus, and then I'm going to pull out of w the very first value, 0.6737. And then I'm going to put that into my first entry of x. My first value of x is going to now get whatever occurs here. Let me erase this. Then I'm going to take what I have just found for x1 and I'm going to change x dot 1 to be this value. So essentially this becomes now x sub 1. Or in other words, well, we'll say x sub 1. Now the second time through this loop, I will be equal to 2. And whatever I get for x1 is going to go there. Take it times 0.7. Then I have w2 here. I'm going to get x2 there. And I'm going to find what that value is. And then I can keep on then setting, well, what I just found for x2 is now going to be x dot 1. And keep on going through this loop. Let's actually change some stuff here so you can better see what's going on. So suppose we just do this loop for 5 different iterations. And what I'm going to do is I'm going to print x dot I through each iteration of the loop. So let me go ahead and do this. So the first time through the loop, I'm going to take 0.7 times x dot 1, which will be 0, and I'm going to add to it w1. What is w1? 0.67. So that's how I got that 0.67. Then this x dot 1 is going to be reset to be 0.67, and then I'm going to come up to I equal 2. When I do I equal 2, I'm going to have 0.7 times 0.067 plus W2, which is negative 0.68. And if you do the math, I get negative 0.6337. The same process continues throughout. Okay. And so this is then what the first few observations look like, and essentially we just saw that as well. And what I'm going to take as my final, let's say, realization of my time series is actually the 101st value through the 200th value that I just simulated. Now, why did I do that? Well, because I don't want, since I had to kind of arbitrarily start the series of data being simulated, since I don't want that to necessarily have an effect of what I'm going to use as my final simulated data set, I decided to chop the first 100 off and just go with the last 100. So then when I do a plot of my data, this is what I get. And what we can see from this particular plot is that, you know, we do see some dependence that appears to be occurring over time. You know, compare this to what we had previously for a white noise process. Here we see the dependence in terms of, like, for example, here we can see that long trend that we're having there. We can see how we tend to stay in about the same spot over time as well. So also here in my notes, I actually go through the mathematical process of which we kind of did as well of how this series actually came about. Now, for some of you, you've probably heard of autoregressive structures or autoregressive models before. And in fact, for those of you who maybe have taken some more advanced classes where you have to set a particular covariance covariance matrix to a particular structure, like you might have with a generalized linear mixed model. You might have heard of an AR structure for autoregressive. And in that particular case, we know that in what we've just done here corresponds to that kind of a structure. And the actual correlation between successive values such as x3 and x2, x4 and x3, and so on is actually 0.7 in terms of a Pearson correlation. And so there's a large correlation that exists. Don't worry about that if you've never seen an autoregressive covariance matrix structure for a model before. Okay, so this autoregressive model here is actually often referred to as autoregressive 1 or AR1 model, because we are using one time period in the past, that x of t minus 1, to help us get to the current time period, or x of t. So people often then use the symbols AR parentheses 1 to represent this autoregressive 1 model. Also, this autoregressive model is one component. It's a building block to a more complicated model that we will see later in the semester called an ARIMA model. ARIMA stands for Autoregressive Integrated Moving Average. That will be essentially a main model that we will examine in this particular course. Since it's a very, very common type of model, people often want to come up with ways to simulate data from this particular kind of model. And instead of using a for loop structure like I just did, there are actually functions in R, one called arima.sim, that will automatically simulate the data for you. You are not responsible for this set of code here yet for our course. I just put it here so that when you review for a test, you can then connect with what we just did with the for loop to something, to another way that we will look at how to simulate data from this kind of a model structure. And I guess lastly here, we look at these plots over the observations over time, and we've simulated data from a particular model. Now, when we actually use time series analysis, we are going to have some kind of observed data set, maybe again the height of a child or the stock price over time. And what we're always going to do is, after we look at that kind of a plot of the data over time, is that we're going to think about, okay, how does this match up with maybe a simulated how does this match up with simulated data in terms of like a moving average or an autoregressive? How does this plot compare to if a situation where I had simulated the data? And so that's part of the process, or part of the reason, I should say, for why we often look at simulated data in a time series course, so we can match simulated instances with what's actually observed for an actual example, so that we can make better sense of that actual example and come up with a model for it. Okay, so with that then, that's a real brief introduction to some of the basic models that we will examine for this course.